Flow stops when the pressure exerted by the weight of the mercury in the tube equals the opposing pressure exerted by the atmosphere on the mercury in the bowl. In other words, the mercury will flow until the pressure exerted by the mercury column is equal to atmospheric pressure. You can determine how much pressure the atmosphere is exerting by measuring the height of the mercury column. At sea level, atmospheric pressure can support the weight of a column of mercury that's about 30 inches high. So atmospheric pressure is equivalent to the pressure exerted by a column of mercury 30 inches high. The height of a column of liquid that atmospheric pressure can support depends on the type and density of the liquid. For example, water is much less dense than mercury. Atmospheric pressure can support a column of water that's about 34 feet high. Atmospheric pressure is commonly expressed in terms of inches of mercury or pounds per square inch. Specifically, standard atmospheric pressure equals 30 inches of mercury or 14.7 psi. A commonly used pressure measuring device is a manometer. Manometers use columns of liquid to measure pressure. This example is a U-tube manometer that's designed to measure pressure inside a container. The manometer is partially filled with liquid and connected to a container that's open to the atmosphere. The atmospheric pressure on each column of liquid is the same. As a result, the liquid level in each column is also the same. Now we'll seal the container and add a compressor to pump air inside it. As the air is pumped in, the pressure in the container increases. The pressure on the liquid in this side of the manometer also increases. This causes a difference in the levels of the manometer's two columns. The difference in the levels indicates the amount of pressure in the container above atmospheric pressure. If air is pumped out of the container, a vacuum is created. That is, the pressure in the container is less than atmospheric. Atmospheric pressure pushes on the liquid in this column, and once again, there's a difference in levels. This difference in levels indicates the amount of pressure in the container below atmospheric pressure. That is, it indicates the amount of vacuum in the container. You can't fully understand how pressure is measured unless you're familiar with pressure scales. Three commonly used pressure measuring scales are the absolute scale, the gauge scale, and the vacuum scale. The absolute scale begins at theoretical zero pressure. Theoretical zero is a condition of no pressure and a total absence of matter. On the absolute scale, standard atmospheric pressure is 14.7 pounds per square inch absolute, or PSIA. The faceplates of pressure gauges that use the absolute scale are usually labeled PSIA. Another type of pressure scale is the gauge pressure scale. The gauge scale starts at atmospheric pressure, not at theoretical zero pressure. So atmospheric pressure is given a value of 0. On an instrument that uses the gauge scale, pressure is indicated in pounds per square inch gauge, or PSIG. But sometimes gauge scale values are expressed simply as PSI. It's fairly easy to convert pressure measurements back and forth between the absolute scale and the gauge scale because the basic unit of measurement for each scale is pounds per square inch. We know that 14.7 PSIA equals 0 PSIG. We can use this information in a conversion formula. Absolute pressure equals gauge pressure plus atmospheric pressure. Since absolute pressure equals gauge pressure plus atmospheric pressure, you have to add 20 PSIG to atmospheric pressure, 14.7 PSIA. So the answer is 34.7 PSIA. 20 pounds per square inch gauge equals 34.7 pounds per square inch absolute. To convert from absolute pressure to gauge pressure, you can apply this formula. Pounds per square inch gauge equals pounds per square inch absolute minus atmospheric pressure. The third pressure scale is the vacuum scale. Vacuum is pressure below atmospheric. Like the gauge scale, the vacuum scale uses atmospheric pressure as its starting point. But the vacuum scale moves toward theoretical zero pressure. The closer it gets to theoretical zero, the greater its value. On vacuum gauges, vacuum is often indicated in inches of mercury. This refers to the level of mercury in a vertical column measured from a level representing atmospheric pressure. In other words, if the level of mercury is 8 inches below the level representing atmospheric pressure, then the amount of vacuum is 8 inches of mercury, sometimes abbreviated inches Hg. If theoretical zero pressure, or a condition of perfect vacuum, could be reached, it would have a value of about 30 inches of mercury vacuum. In this topic, we focused on the measurement of pressure. We saw how atmospheric pressure can be measured, and we learned how manometers indicate pressure. We also looked at commonly used pressure scales. Take a minute now to try a few practice questions on this material. Atmospheric pressure is related to height or depth. That is, the pressure of the atmosphere varies with the height of the air above the Earth's surface. For instance, atmospheric pressure at sea level is greater than atmospheric pressure at higher altitudes. If air is pumped out of the container, a vacuum is created. That is, the pressure in the container is less than atmospheric. Atmospheric pressure pushes on the liquid in this column, and once again, there's a difference in levels. To convert from absolute pressure to gauge pressure, you can apply this formula. Pounds per square inch gauge equals pounds per square inch absolute minus atmospheric pressure. This topic explores some of the principles related to flowing liquids. We'll look at flow and flow rate, and we'll see some of the effects of flowing liquids. To view the entire topic at this time, select the View Entire Topic box. To view only a portion of the topic, select the box of your choice. Virtually every system in a process plant contains flowing liquids of one kind or another. Flow occurs when liquid moves. The amount of liquid that is moving and the time it takes to move from one place to another can be measured. These measurements give us a liquid's flow rate. Flow rate can be defined as the amount of liquid flowing past a given point per unit time. To determine flow rate, we'll assume that steady state conditions are in effect. This means that conditions at any given point in a system remain constant with time. In other words, we have to assume that such factors as pressure, temperature, and flow do not change from one second to another. With this in mind, let's take a look at one way to determine the flow rate through a pipe. This illustration represents a section of pipe and a volume of liquid. This dashed line represents a given point in the pipe, as well as the cross-sectional area of the pipe. As you'll see, this area is necessary for our flow rate calculations. When the liquid passes a given point in the pipe, it travels a certain distance in a certain period of time. That is, it has a certain velocity. The flow rate is calculated by multiplying the cross-sectional area of the pipe by the liquid's velocity. In this case, the cross-sectional area is 0.35 square feet, and the velocity is 10 feet per second. So the flow rate is 3.5 cubic feet per second. We used a simple example to introduce the basics of flow rate measurement. In the plant, you'll often find that flow rate is measured in different units, such as gallons per minute or pounds per hour. To understand the effects of flowing liquids, you need to know about a property called head pressure, or simply head. One example of head is the pressure exerted by a column of liquid as a result of its height or level. The amount of pressure exerted also depends on the liquid's density. Denser liquids exert more pressure for a given height than less dense liquids. Another way to explain head is by looking at the relationship between two different pressure measurements, pressure in pounds per square inch and pressure in feet of water. Let's take a look at an example. Atmospheric pressure is 14.7 psi. Atmospheric pressure can support a column of water about 34 feet high. In other words, atmospheric pressure in feet of water is about 34 feet. If we compare atmospheric pressure in psi to atmospheric pressure in feet of water, we find that each foot of water equals 0.433 psi. In other words, a column of water 1 foot high produces a pressure of 0.433 psi. If a pressure gauge were placed at the bottom of this column of water, it would read 0.433 psi. Head is normally expressed in units of feet of liquid, so for water, 1 foot of head is equal to 0.433 psi. Now we're going to turn our attention to some of the effects that flowing liquids can have on head. To help demonstrate these effects, we have a tank of water connected to a simple piping system. This system has 3 standpipes. At the moment, the water's not flowing, So conditions in the system are said to be static. Under static conditions, the levels in the standpipes are the same as the level in the tank. However, when the water is flowing, conditions in the system change. When the water starts flowing, the levels in the standpipes drop. Now they're lower than the level in the tank. So when there's flow, the levels are lower than they were under static conditions. Also notice that the levels in the standpipes are different. To understand why these changes occur, we need to look at three properties of liquids: static head, velocity head, and friction head. Static head is related to the level of liquid. Velocity head is the change in static head due to velocity. And friction head is the change in static head due to friction. Friction is a force that opposes motion. Under static conditions, velocity head and friction head are zero because there is no flow in the system. But when liquids flow, some of the static head is converted to velocity head. As a result, static head is reduced and the level in the standpipes drops. As velocity increases, static head decreases and the level in the standpipes decreases. As velocity decreases, static head increases and the level in the standpipes increases. To better illustrate the ideas, we'll exaggerate the level changes in the standpipes. Even when there's flow in the system, the liquid in the standpipe still exerts static head. The level in each standpipe is the static head for that pipe. But the difference in the levels is due to the change in static head caused by velocity and friction. The difference in level between the tank and the first standpipe is a result of the velocity of the liquid and the friction between the tank and the first standpipe. Assuming steady-state conditions, the velocity is the same through the horizontal pipe. Therefore, the different levels in the standpipes are a result of the friction in the piping between the standpipes. The decreases in levels represent the decreases in static head caused by friction. The effects of friction increase as the liquid flows through more pipe. Friction in a flowing liquid can come from a variety of factors, including the liquid's viscosity or resistance to flow. Friction can also come from the adhesive forces between the liquid's molecules and the walls of the pipe, and from the turbulence of the flow. In this topic, we examined some of the important properties related to flowing liquids. We looked at the principles behind flow and flow rate, and we saw some of the effects of flowing liquids. Take some time now to answer a couple of practice questions. The flow rate is calculated by multiplying the cross-sectional area of the pipe by the liquid's velocity. Assuming steady-state conditions, the velocity is the same through the horizontal pipe. Therefore, the different levels in the standpipes are a result of the friction in the piping between the standpipes. The decreases in levels represent the decreases in static head caused by friction. The effects of friction increase as the liquid flows through more pipe.